Alright, before ending section 2, there's a type of question that I want to introduce you guys to and go over it. And it's an applied type of question trying to find out whether you really do understand what's happening with the neuron and neuromuscular connections and just synaptic connections in general. So here's our example. So a drug, right here, I'm not going to even try to pronounce it, is a potent acetylcholine esterase inhibitor used to treat patients with Alzheimer's disease. If applied at the neuromuscular junction, would this drug enhance, suppress, or have no effect on calcium influx in the muscle cell? Now, initially when looking at this, you might not know where to start, but let's just look at how muscle contraction occurs. So we have an action potential, which arrives at the presynaptic membrane. That leads to depolarization of the presynaptic membrane. And this leads to voltage-gated calcium channels opening. Remembering that all these arrows are activation steps. And this leads to acetylcholine release into the synaptic cleft. And of course, these acetylcholine concentrations in the synaptic cleft are inhibited by acetylcholine esterase. Acetylcholine will activate acetylcholine receptors on the postsynaptic membrane or the end plate. This will lead to depolarization of the end plate. And of course, depolarization leads to activation of voltage-gated sodium channels. And these are also on the end plate, and this is a positive feedback loop on depolarization. This leads to voltage-gated calcium channels on the end plate to be activated, meaning they're open. And of course, when these open, this also leads to the calcium release channels being open. And both of these will lead to calcium being released into the cytosol. So the activation of calcium is calcium concentrations going up in the cytosol. And this leads to muscle contraction. So when we're looking at this and we're saying that our drug is an inhibitor of acetylcholine esterase, which is right here, that means that we are removing this inhibition, right? Or at least we're kind of making that inhibition not as much as it was before. So if you remove that inhibition, then acetylcholine concentrations in the synaptic cleft go up, acetylcholine receptor activation goes up, depolarization goes up, this goes up, this will go up, this will go up, calcium release will go up, muscle contraction will increase. Now the question is whether this drug enhances, suppresses, or has no effect on calcium influx into the muscle cell. And that is right here. And it will enhance it. Right? So that's the answer. That's how you come to that answer. Now you can think of many other things that a drug might activate or inhibit. For example, let me get rid of these. If my drug inhibited acetylcholine receptors, then I could say that, well, my drug is inhibiting acetylcholine receptors, so the activity of acetylcholine receptors goes down. Depolarization decreases. The voltage-gated sodium channels, of course, decrease. This decreases. This decreases. And this decreases. And my C has left the building. And that will decrease muscle contraction, right? So if the question says, does it have an effect on, for example, acetylcholine release? Well, acetylcholine release is upstream, right? Not downstream of where the effect is happening. The effect is happening at acetylcholine receptors, so there is no effect. But if the question is saying, does this affect depolarization of the end plate? Well, the depolarization of the end plate is happening here, so it would decrease or suppress the depolarization of the end plate. So with these type of questions, you just have to see where the drug is affecting the system, because the system is moving in a very linear fashion. And you just kind of go, okay, well, it's affecting here. Everything downstream is going to be affected, whether that's a positive effect or a negative effect. And you just go along and you put those arrows. If it's an activation, it's going to increase the downstream effects. If it's an inhibition, it's going to inhibit the downstream effects, but it's going to leave the upstream events happening unchanged. Now the next thing I want to talk about is that without the AIS, what will happen is as long as the PSP is past threshold, action potential is being fired at max frequency for that neuron. So you have to sort of keep that in mind, what the AIS is doing. The AIS is simply making sure that if the signal is weak, you make that membrane more permeable to potassium to slow down the frequency of action potentials being fired. Otherwise, without the activity of those rapidly inactivating potassium channels, what will happen is that as soon as the PSP is past threshold, you'll get maximum signal being sent down the neuron to this whatever cell it's synapsing with. That's what the AIS is doing. Another topic that I want to touch on is the strengthening and weakening of single synaptic connections. So there are these molecules called neuromodulators. They have an overall effect on parts of the neurosystem. Now, that being said, even single synaptic connections, so we're going to draw out a synaptic connection here, and of course our postsynaptic membrane here, and presynaptic here, and synaptic cleft between them. Depending on the history of the synaptic connection, the single synaptic connection can strengthen or weaken. And what does that mean? Well, there's a couple of things that can be done. Now let us assume that once an action potential arrives at the presynaptic membrane, every time that membrane is depolarized and there's voltage-gated calcium channels open and let calcium in, you're going to get diffusion of the same amount of neurotransmitters no matter what. So the amount of neurotransmitter doesn't change. But then you have the transmitter-gated channels. So let's just put some. And I'm just going to draw these as rectangles. Okay, so we have these transmitter-gated channels here that are going to be specific for whatever the neurotransmitter is that is being released. And our neurotransmitter will be in green. We'll just put 5 dots, and they will bind to these transmitter-gated channels, and they will allow those transmitter-gated channels to go to the open position and conduct whatever they're going to conduct. Whether it's an inhibitory neurotransmitter, where you're going to get these transmitter-gated channels that will make the membrane permeable to Cl- or potassium, or excitatory, where they're going to make it permeable to sodium, or their cation channels. If the amount of neurotransmitter can change, well, what you can change to make the membrane either more sensitive to neurotransmitter or less is by increasing or decreasing the amount of transmitter-gated ion channels that are at that synaptic connection. And the cell does that. Because what is the relationship here? We have neurotransmitters, we'll just say NT, plus transmitter-gated channels, so we'll just say transmitter-gated channels, right? This binding reaction will give us the transmitter-gated channels and NT bound to each other. Now, of course, this interaction has a Ka. So Ka of this would be the concentration of transmitter-gated channels bound to neurotransmitter over the concentration of neurotransmitter freely floating in the synaptic cleft and transmitter-gated channels. Now, if I increase the amount of transmitter-gated channels by some amount, I have to increase the number of bound by the same amount. So by just increasing the number of transmitter-gated channels on the membrane, I make the membrane more sensitive to the neurotransmitter. What does sensitive mean? It means that at the same concentration of neurotransmitter, I will have more transmitter-gated channels bound with the neurotransmitter. Let's actually draw another synaptic connection here. And we're going to have only 2 transmitter-gated channels and the same amount of neurotransmitter. Now the one here is less sensitive than the one over here. And that is simply because you have less transmitter-gated channels on that membrane, on that patch of membrane, on the left than you do on the right. Since you have more transmitter-gated channels on the right, even though you have the same amount of neurotransmitter, you're going to get more complex formation. What we mean by sensitivity is that at equal concentration of signaling molecule, in the case of synapses, it would be neurotransmitters, one patch of membrane will be activated more than the other. And the way you do that is by increasing the receptor or the transmitter gated channel levels on that patch of membrane. And what is happening in your synaptic connections all over your body is that single synaptic connections, not all of them, single synaptic connections can be weakened or strengthened through this mechanism. This is one mechanism by which they can be weakened and strengthened. And that adds to the complexity of the nervous system. Now, one other thing I wanted to talk about, which even adds more complexity, is the idea that a single inhibitory connection can supersede all excitatory connections, or most of them. So, for example, if I have a neuron that looks like this, right? And of course, on the right side, you're going to the nerve terminals, to the axon terminals. Well, if I have an inhibitory connection, synaptic connection right here, so this is inhibitory. Well, even though the cell might be receiving excitatory connections elsewhere, if there's a lot of EPSPs coming into the rest of the soma and dendrites, if this inhibitory connection is excited to a large amount, high frequency action potential is coming down to it, well, then this whole area becomes hyperpolarized, meaning it becomes permeable to potassium or Cl-. And the AIS is somewhere here, right? So essentially, this connection can supersede or trump any of the excitatory connections coming into it. The complexity of nervous system, there's no bounds to it. And the way these synaptic connections are made, the inhibitory and the excitatory, leads to one action or one excitation of a certain neuron overriding the excitation of other neurons. Alright, that's all I wanted to talk about. Okay guys, thank you.